Okay, let's tackle part 2 now of this problem, basically, for the hydrogen atom now. I know we did the particle in a box, and we basically find the quantizations and all of the problems. So I'm going to write Schrödinger's equation now in the polar coordinates, not in the Cartesian coordinates, and it looks awful. I'm quoting in here Feynman. So first of all, the potential now is this is the electrical potential. So this is basically U. Why is it not writing? Okay, is equal to minus E squared. Not the electrical potential in the sense of V. This is EV. This is the actual energy. This is the potential energy. Okay. We have basically the model that we're going with is for the hydrogen atom. We have a proton in here of a positive charge E and a negative charge E, namely for the electron. And we're going to use something called the center of mass, basically representation, because in fact what we have going on in this problem is that both particles, because of the heavy weight of the proton, actually they oscillate around their they move around their center of mass. So if we do that, since the mass of the proton is almost 2,000 times bigger than the mass of the electron, the idea here is that the reduced mass will be very, very close from the mass of the electron. So this is the mass of the electron, the mass of the proton divided by the mass of the proton plus the mass of the electron. And this is about 10% correction in the values that we apparently have had difficulty with trying to reconcile with even in the model for Mr. Bohr. He had to introduce the reduced mass. So in this approximation, of course, MP is very large. I'm going to use roughly 2000, okay? So this is roughly about 2000 MP and the mass of the electron divided by 2001, okay? 2001. The same mass of the electron. I have here squared. So this one cancels that, and that is basically how we come up with the value. It's actually less than 2000. To be more specific, but I'm just roughing the number in here. Anyway, so the mass that we're going to use at the end in the equation is not going to be that of the electron, but very, very close from it. That is the reduced mass. Otherwise, we'll get slightly different answers. Anyway, the potential energy has a 4 pi epsilon naught divided by R. Okay, so this is basically the potential energy for this problem. Because R, technically, if we're going to use the polar non-polar coordinates, is going to be this parameter. The problem could be very complicated, and it's really not useful to use it in Cartesian coordinates, as I was saying. So we're going to use a function now, and we're not going to actually solve this one, but I'm just giving you an idea of how this goes. So the function now, in this case, is going to be, instead of depending on x, y, and z, we're going to use the polar coordinates r, theta, and phi, and actually we're going to separate it right there and there to a component that is radial, a component along the direction theta. So this is the angle theta. Capital theta in this case is the function, and little thing is the variable in here, times phi as a function of phi. So basically this is the separation that we're going to end up with. If we do that and use how basically the operator del squared looks like in polar coordinates, which is quite involved actually. For one thing, the angular component for it, I'm trying to find basically the actual, I don't memorize it, and it's a very, very lengthy derivation for it. Let me find the book for Feynman. If you want to follow this calculation, it's a good idea to look at the 3rd edition of Feynman lectures, and I'm trying to see, I think it's chapter 19 from the book, where he did the actual solution of Schrödinger's equation for the hydrogen atom for the case of the S shells, and it is really very nice derivation so that you can understand all of the things in it. Where is chapter 19? I'm sorry, I'm looking for, yes, chapter 19. Where is the del operator in here? If you have time, you could go through the derivation yourself on how to convert this del, and it's a messy job. I tried it before, even for the case of the 2D, which is kind of straightforward, but it really took about 2-3 pages to do. So anyway, this is something I don't remember. I don't know if you really need to remember it. So this is applied to any function f in this case. I'm just going to follow the notation of Feynman. So it's 1 over r times the second derivative in here, and you have to be very careful in here. It's not the derivative of f by itself, but actually r times f. Okay. So there is a part in here where there is cancellation, and you will only have the second derivative with respect to r, and there is another term that is going to be added in here. Plus, I'm going to follow another notation in here, a little bit different than Feynman. 1 over r squared times the L squared, where L in this case is another function, another operator, which is a so-called Legendrian operator, just similar to the Laplacian basically, except that it includes in there and it's just the angular component of it. The reason why I want to write it this way is because of this r squared that complicates situations big time. But in the situation, this is 1 over sine of theta. This is the other, if you wish, part that is needs to be done. The derivative with respect to theta of sine theta, the derivative with respect to theta again of the function f again. Okay. Oh no, I'm sorry. I'm just writing it without any function here. If you wish, we can reintroduce f in here, and it's going to have an f in here that is applied to it, this operator again. Okay. And this whole derivative is on that, plus another term actually that involves the derivative with respect to phi, which is 1 over sine squared of theta, the derivative of f with respect to phi. It's quite long, and it's really not pretty thing to look at. But the idea in here is that you could separate the problem into 3 basically different equations. One involving the dependency on the longitude, and the other one involves the dependency on the latitude, and the last one is on the radial dependency. If you take the S basically mode, meaning that the function at the end, function psi does not depend on theta and phi, it depends only on r. If you do that, then these derivatives of course are 0, and this one is 0, and you'll be left just with this problem plus this potential, so that you have the equals to basically the energy times the function psi. So what you end up with in this case is just a differential equation for that part, and you should be able to find the different states for it. And you will find that immediately that the energy is quantized, and it has to be quantized because you will have 2 solutions. One solution that explodes exponentially, and another solution you can actually cancel this exponential growth, this exponential basically explosion, which when you calculate the probability of where the electron is going to be, you will find that it's always trying to get away from the proton, and that doesn't make sense. So we needed a correction to this one by terminating the sum, and when we terminate the sum, we will find that the energy in this case needs to be quantized. So this is in a nutshell how the solution goes. Okay, so if we separate the equation, even in this form, okay, in this level you're not really required to carry the actual calculation, but at least to have a flavor of how it looks like. Okay, so what we have in this case, so the radial component is of course a straight derivative. We don't deal with partials anymore. So it's going to have this minus h bar squared over 2m, r squared in it. You have to divide by r squared and multiply by it so that you can get rid of this r squared in the Legendrian. The solution to this one is actually the so-called Legendre functions, okay? And it's a combination of theta and phi, and it's really a polynomials that involve trig functions. And that too requires quantization. That's where we get the condition of the angular momentum. In this case, L being basically restricted between 0 and n minus 1, where this will give me the n. And then also the m, which is for the other one, has to be restricted in a sense to be between 0 and plus or minus 1, plus or minus 2, all the way to basically plus or minus L, depending on where you are. So we're going to get to that idea in here. So again, the mass in here I should be using really as a reduced mass, not the full mass, not the mass of the electron. And that is the derivative with respect to r of r squared, the derivative of r with respect to r, okay, plus h bar squared times L plus 1. So where did that L pop up from? It popped up from the other operator, okay, because we're separating the variables, so we need to keep the connection between them, divided by twice the mass of the reduced mass, in this case r squared. This is where that r squared is coming from, and plus a potential. The whole thing is multiplied by r is equal to ER. Okay, and the other two do not involve the potential energy. Therefore, they're just basically functions in the with respect to theta and phi. And they are basically, the first one is quite actually a function 2. I mean, quite an equation 2. So 1 over sine of theta. The derivative with respect to theta. I should really write this theta because this is a variable theta, of sine of theta, the derivative of theta with respect to theta. Oops. I don't know what happened to my OneNote. It crashed on me. I think it saw so many differential forms in here, it's not even liking it. But anyway, so again, we have 1 over sine of theta. This is theta as a variable theta, not the function theta. The derivative with respect to theta of, again, sine of theta. The derivative of theta, the big theta, with respect to the variable theta, okay, plus open parentheses L times L plus 1 minus m, I'm going to write it z. I know the book writes it L, but I'm going to write it z, and you will see shortly why, divided by sine squared of theta as a function of theta. So this is the big theta, okay, as a function of little theta is equal to 0. So the eigenvalue in here is just the ones that are giving me just the 0 in this case for the function theta. And so is actually for the for the phi, it's a very easy equation. It's like that of the harmonic oscillator. So this is the phi with respect to phi, okay, plus mz squared. Again, I'm doing slightly different notation in here than the book. Phi of phi, phi of, not theta in here, I'm going to go of phi is equal to 0. Obviously, the last equation is just periodic functions. And this gives me an immediately a restriction on these periodic functions in a sense that they have to be actually periodic. And the reason why they have to be periodic so that the function is actually a single valued function, because if I want to integrate it, I have to have an integral for it in order to explain what that integral is. I mean, it has to do with the position of the particle, of course, and the probability to give it the interpretation basically that we promised in the beginning, that it's the density, the density probability function, because when I square it, basically when I take the modulus square, because this is actually a complex function also still, so the solution for phi is a constant times an e times I mz phi plus another constant which is exponential of minus mz of phi. So this equation in here better be periodic, and in doing so we'll find the condition on mz, and mz then in this case must be times 2 pi must be equal to must be multiples of pi. So mz phi is equal to some integer times pi, or in a sense in here, exponential of I mz times 2 pi must be equal to 1. So for that, that means that mz can only be 0, plus or minus 1, plus or minus 2, and so on and so forth, okay? Because if I move this function by 2 pi, I should really keep the same value, at least when I go full circle along the longitudinal direction, okay? So this is actually an mz in here. It has no restriction. The only problem in here is actually limited by this L. So in this case, it's going to be limited at plus or minus L. Furthermore, and I'm not going to show that one because again, it really involves a lot of mathematics and a lot of functions that are beyond the scope of this course. But the point in here is that the L itself is actually restricted between 0, 1, and all the way to n minus 1. And n in this case is the restriction on the energy itself, the eigenvalues of the energy. As a matter of fact, the energy will turn out to be exactly given by the Bohr's model energy, which is in this case En is equal to minus, and the minus in this case has no mysteries in it other than the fact that we took the, when the particle is free, has no energy at all. In this case, it can, I mean, it has no potential energy at that point, so far away from the proton, the electron can move freely at that point. So when it's near it, of course, it's retained to it, and that's what the negative is. This is no different than what you guys did in the case of gravitational energy of a satellite, for example, or planets or things like that. So 4 pi epsilon naught. This is epsilon naught has to do with the basically the permittivity of the beats of the vacuum times because we're assuming this is a vacuum. Mr, the reduced mass in this case, and again, even in the Niels Bohr model, we had to really actually use Mr instead of M for the electron, e to the power 4 divided by, again, 2 times n squared h bar squared. This is exactly minus 13.6 electron volt, so provided we keep only one of these e's in here in the calculation, because the other one is just converting joules into electron volts, and this is the value of n. Where n now can be any integer from 1 to whatever number you like, 1 being the ground state. So n can be 1, 2, and 3, and so on and so forth. So this is the picture that is emerging for this ground state stuff in here. The momentum in this case, the angular momentum in this case, L, is, so this is the angular momentum, is given by L, which is just that square root of L times L plus 1 times h bar. And Lz itself will be just basically mz h bar, okay? If you're curious, try to find where this came from in here, and if you want to remember, if you remember from mechanics that the vector position r crossed with p is going to be the momentum in general L. So what you do in this case, you take the Lz component, which is just going to be, if you do the how to find the cross product, you guys remember this is x, y, z, and it has to be in this order, by the way, otherwise we'll get a negative number. And if I do the conversion to quantum mechanics, actually, the momentum, the px coordinates again is h bar over I, the partial derivative with respect to x, h bar over y, I, times the partial derivative over y, and h bar over I times the partial derivative of z. So I know I mentioned that before, and this is basically how the momentum is expressed in Cartesian coordinates again. And you're wondering what happened. Why are we using Cartesian coordinates? Don't worry about that. It's just to show that in polar coordinates this has a lot simpler version of it, and actually it's going to be exactly equal to, again, what is it? The x times py minus y minus. We're looking at this one, so minus ypz, basically we took the direction of the magnetic field that is applied in here in some direction, which we called it the z direction. So in this case, the only significant component for the momentum is going to be, for the angular momentum is going to be along the z direction. Okay. So if I do the calculation in here, I'm going to take, for example, b equal to 0 in my phi. So the only thing of interest right now is this one, the b equal to -0, the b equal to 1 and the a equal to 0 is going to be a different solution, but it's going to be just basically the other component flipped back, and that's it. So the LZ in this case is going to be this operator, and if I use the coordinates, I'm going to do it just in 2D because it doesn't matter now, since we're just restricting the particle to talk about its angular momentum in the z direction. So in this case, the coordinates in the x and y plane are simply given by of any vector in here in this particle that is moving on this direction. So it's going to be basically x is equal to r cosine of phi, and y is equal to r sine of phi. So if I do the conversion correctly in this case, so this is x that I'm going to plug in there, and this is y that I'm going to plug in there. And furthermore, I'm going to simplify a little bit the problem in here, because actually when we're doing this problem for the phi, it doesn't matter where the particle is in terms of its distance from the proton. So we're going to assume that r is constant just to simplify the calculation. But if you don't want to do that, that's fine too. You're going to find the same result. So if r is constant, then we can do this. If not, then we just do the full-fledged derivation, which means that py, remember, which I wrote it as h bar over I times the partial derivative with respect to x, is going to be written now in polar coordinates as h bar over I times the derivative of first of all r with respect to x times the derivative with respect to r plus the derivative of phi with respect to x times the partial derivative of with respect to phi. I did not want to do this, but just to give you an idea of how this converges, how you write this one in here so that you can get the correct answer, is that okay, what is dr with respect to x? If you notice, dr with respect to x, this is px, then I'm not writing py, I'm sorry. Okay, because I did the derivative with respect to x. Py is going to be the same thing, by the way. It's just change this one to y, this one to y, and this one to y. So r is, in this case, is x squared plus y squared. If you care to do the whole thing, you can, okay? But what comes from this derivation in here of r with respect to x is simply the derivative of under the square root in here, it's going to be 2x divided by 1/2 coming from the power that is of the everything in here, so the 2 and the 1/2 cancel, and divided by this x squared plus y squared to the power 1/2 minus 1, which will become in the denominator. So the answer is x over r, or simply equal to cosine of phi. Okay? Then the same thing in here, you're going to need d phi with respect to x. For that, you notice that tangent of phi is equal to y over x. So that means that if I take the derivative of both sides with respect to x, so on one side it's 1 over cos squared of phi times the derivative of phi with respect to x must be equal to the derivative of this side with respect to x, which is simply minus y over x squared. And that is going to be minus r sine of theta over r squared cos squared of phi. And the reason why I'm using just this transformation between the x and y coordinates on the plane, because I'm just focused on the LZ in here. So in other words, this is simply cancel the r squared, cancel the cos squared and the cos squared. So that means d phi over dx is simply equal to minus sine of theta over r. Okay, and this is basically how you do that whole transformation to get into this mass anyway. I mean, I'm just giving you a flavor of how this looks like. So this will be the dx. So the dx is going to be, the px, so I'm sorry, px is going to be h bar over I times the derivative times cos phi, the derivative with respect to r, plus, minus in this case. The reason why it's minus is because I pulled up a minus in here, sine of theta over r times the derivative with respect to phi. And if you do the same thing for py, I'm trying, let me see if I can do it by symmetry without actually having to do it. So it's going to be h bar over I. First of all, there will be a plus in here, not a minus. And I think it's going to be a cos phi, there is no theta in here, cos phi over r, the derivative with respect to phi, and in here that will be a sine of phi, the derivative with respect to r. I think that's the correct one, because when I take the derivative of this other side, it's just 1 over x. Okay, so this is now, all you have to do is just multiply this one by x, which is r cosine of phi. So it's going to be r cosine squared of phi, and so let's do it. Let's find what this thing looks like anyway. So let's find LZ now. LZ is equal to xpy minus ypx. You see, I almost made a mistake in here, big time. Okay, x times this number, and x is r times sine of phi times cosine of phi. So it's going to be h bar over I. I'm going to take that the whole thing in here. So what you have in this case is r times sine of phi cosine of phi. This is the sine of phi, and this is actually x, times the derivative with respect to r, plus r cancels r, so I'm left with the cos squared of phi, the derivative with respect to phi, minus y, which is r sine of phi, times this one, so it's going to be r sine of phi cos phi, the derivative with respect to r, minus times minus is going to be a plus, and it's going to be r cancels the r, and you will be left with the sine phi coming from y times sine squared. Sine phi is going to be sine squared, so it's going to be a plus, because minus times minus is a plus, sine squared of phi, derivative with respect to phi. Okay, this cancels, and it's very important, because even in the case when r is changing, this term cancels, and that's very important, because this is LZ in general, regardless of whether or not you have a particle that is traveling on a circular path basically and restricted to it, or a particle that can travel anywhere. So the angular momentum in the z component, where we are going to apply the magnetic field, does not depend on the radius, and the cos squared plus sine squared is 1. So in the end, the angular momentum LZ is simply equal to h bar over I, the partial derivative with respect to phi. If you take b equal to 0 again in that expression, when I take the derivative with respect to phi, I'm going to drop an I, and I'm going to drop an mz. So I cancels the I, so this then LZ of that solution of phi is simply going to be h bar over I times I mz times phi itself, because the derivative of the exponential is actually an exponential. The I cancels the I, and it's very important that the solution to this problem in here is mz h bar. And this is how we know that actually the component, this is actually an eigenvalue problem. That means that this is the eigenvalues of this angular momentum along the z direction, in that this is its value when you actually do a measurement. So mz, the one that we found, and it's restricted, is actually the eigenvalue problem for the component along the z direction. So the angular momentum by itself is equal to square root of L times L minus plus 1 times h bar, and the value for the one in the component this direction is just mz times h bar, as I was saying. To give you an idea of how this works, let's take some cases now. Let's take n equals to 0, the ground state. I'm sorry, there is no n equals to 0. That doesn't make sense. N equals to 1. For this one, the only values possible for L are 0. And the only value that follows then in this case is mz equal to 0. So in this case, the angular momentum in this case is 0, and the its component along the z direction. So this is actually a radial solution, a pure radial solution. It does not depend on theta or phi. And this is one of the solutions that you can actually work out the algebra for it. Followed Feynman lecture on the 3rd edition, chapter 19, and you should be able to find the solution. It's not hard to follow. Anyway, I probably should do a video on sometime in the future on that, on how to basically rewrite it if you wish. Okay, let's take the case of n equals to 2 now. That is interesting. N equals to 2. We have two possibilities. Either L is equal to 0 or L is equal to 1. Remember, it's 2 minus 1, which is 1. So in this case, mz is equal to 0. Again, that is actually something that you can derive, and that's actually in that chapter. Mr. Feynman found the solution for up to n equals to 3, which is very nice, okay? And you can plot them and things like that. So for this one now, I have three values for mz. I have mz equal to -1, or 0, or 1. Okay? So those are the three components for that vector for n equals to 3 now. We have L equals to 0, L equals to 1, or L equal to 2. For this one, we only have mz again equals to 0. This one, we're going to write mz now can be three values, -1, 0, and 1. And this one, mz, actually is 5 values, -2, -1, 0, 1, and 2. Okay? So again, now we have degeneracy as we were talking about earlier, because each and every one of these numbers represents a state. So the combination of n, l, and m, z is actually a state in this case. So let's take one of them. Let's take this case, for example, for n equals to 3, l equals to 2. In that case, the angular momentum, the value of it, if you wish, if you do an experiment in here and try to find its value, it should be around square root of 2 times 2 plus 1 times h bar, okay? So in this case, it's going to be square root of 2 times 3, which is 6 times h bar. Lz now can have several values. Can range from -2 times h bar all the way to +2 times h bar. 2 times h bar, because square root of 6 is more than 2 actually, can be interpreted as a component basically of the vector along the z direction. So if you look at the momentum, the angular momentum in this case, so this is the full value on the x-axis, on the y-axis, on the z-axis, I'm sorry. So this is the full value on the z-axis, and that is square root of 6 times h bar. I'm going to drop h bar for a second in here because it's the... So the first value in here is the value L equals to 2. Then followed by L equals to 1. Then followed by L equals to 0. Then L equals to -1. And then L equals to -2. Those are basically the three different components in here of the momentum. This value, all of the length should be the same. They're square root of 6 times h bar. So this value in here should be 2 times h bar with a negative sign. This should be -1 times h bar. And this should be 0. And this should be 1 times h bar. And this should be 2 times h bar. Okay? And there is a reason why this has to do like this, is because of the uncertainty principle actually. And the uncertainty principle cannot basically fix the value in here in the z direction, where you know that the particle then in this case will be moving in the xy plane. Again, that is basically something that has to do with the uncertainty principle to satisfy it still. Now, of course, you can find these angles if you really care for it. Okay, what is this angle? Remember, theta is measured from the z-axis. Okay, theta is 0 along the z-axis. This theta is 90 degrees, by the way. Okay, and theta varies from 0 to 180 degrees and vice versa. So in this case, arc cosine of theta is going to be simply equal to 2 divided by square root of 6. Okay, in this case it's going to be 1 divided by square root of 6. So the first angle should be something, I think, like 35 degrees, and the second angle is like 65 degrees, and the third angle, of course, is going to be 90 degrees, and the others are just added 90 degrees to the existing numbers, and you should be fine. So this is what we are headed now. Okay, this is where we look like now. Okay, looks like in every single energy level we have the three values in this case for n, L, and M. We call the level basically, so first of all, the energy levels are determined by n. N is the shell in this case. So n is equal to 1 is the K shell. So this is a representation of the so we're not really doing calculations in here trying to find what this wave function look like, although I refer to the book of Feynman where you can see it for the S states for up to 3. But more than that is going to really be ugly and looking not pretty. But the representation that we're going to do in here is just to follow the quantum numbers, similar to the problem that we did before for the particle in a box. Okay, all we needed to really keep track of was those quantum numbers n, x, and y, and z. Okay, and in here too we have, like I said, degeneracy. So in this case, for n equal to 2, it's the L shell. For n equals to 3, it's the M shell. And for n equal to 4, if you ever need it, it's the N shell. Okay, so this is the shell representation. Now, in each and every one of them, I have 3 values. I have 2 possible values for L. L can be 0, or L can be from 0 to n minus 1. So in this case, I only have L equal to 0. Okay, and mz equal to 0 in this case. So this is what I'm going to call the S state. Okay, and in this situation we have 2 possibilities: either L equal to 0 and mz equal to 0, and this is also another S state from the L shell, or we have another possibility that L is equal to 1 now, and mz can potentially be equal to 0 or plus or minus 1. So this is the P state, okay? Or P states in this case, because you have a bunch of them, okay? Now, if we follow this argument in here, then we are going to have an L equal to 0, mz equal to 0, and this is the S states again. And this is another one similar to that one, L equals to 1, mz can potentially be 0 plus or minus 1. And this is the P states. Now we have another configuration where L is equal to 2 and mz can be potentially 0 plus or minus 1 and plus or minus 2. So this is the D states. Okay. Finally, for this shell in here, we have L equals to 0, mz equal to 0. That 2 is the S states. And in here we have L equal to 1 and mz can only be 0 or plus or minus 1. So in this case we have the P states. Another possibility in here, L is equal to 2, still mz is equal to again 0 plus or minus 1 plus or minus 2 plus or minus, yeah, that is the D states. And finally there is actually another one in here, that is L equals to 3, mz can be in this case 0 plus or minus 1 plus or minus 2 plus or minus 3. So this is the F states. So you're wondering, what is this letters in here, S, P, D, and F? Why do we have to use them? Why don't we use A, B, C, D? Well, it has to do with the spectroscopy, because we want to match this data with the spectroscopic analysis and data that we used to have from different graphs. Anyway, so this is in a nutshell. I know I mentioned for you guys to look at the problem, to look at the actually it's in the textbook too. So once you find the 3 fundamental levels, you can actually square them and find the averages in there. It turns out the n equals to 1, L equals to 0, mz equal to 0 state is proportional to the radius, in this case exponential. It does not depend on theta or phi. So there is a parameter in here, alpha times r, or alpha in this case just has a dimension of 1 over distance. And this is the wave function basically in a nutshell, okay? There is a constant in here that I did not write. And usually I don't know what to say about that constant. I know there is a big fuss over the normalization, and you can normalize this function, ensure that psi squared in this case from 0 to infinity, this integral in this case over a volume, by the way, in here. So there is a 4 pi over 4 pi r squared over r. So this must be from 0 to infinity for the entire space basically. Okay. So this integration here, 4 pi r squared dr. Okay. So this integral must be 1, okay? And so that's how you find that constant. If you don't want to do that, and there are people who actually do not really make a big fuss over that, is that don't forget then when you're looking for an expected value, for example, where the electron might be, okay? So if you're trying to locate the electron on average, so what you do in this case, you're going to find its average for this S state. This is the S equal to S state for n equals to 1. And L equal to 0 and mz equal to 0, okay? So this is the solution. If you want to find the average, the position of the electron in this state, you will find that basically, if you don't do the normalization, is that you divide by that integral end of the story, okay? Because that's the purpose of the normalization, so that you don't do this integral several times. But in here, you're going to find the integral basically, don't forget this is just the radial integration. There is a 4 pi, here is a 4 pi, okay? A solid angle. So in this case, here is an r times this whole thing, dV, okay? So that's how you find the average. So it's a weighted average actually, and this is the expectation of the any measurement, in this case the position of the electron. Okay, so if you do this calculation, you're going to find the value that is not necessarily near center. Although function, this one looks like it's centered near the origin. Okay, so the function itself side really does not have any meaning except when you do this integrations in here for it. Okay, and you will find that actually it immaculately gives you the number that Mr. Niels Bohr also found for it. So that is really how this whole thing is about. Now let me talk about the Ziman effect and talk about why this makes a lot better. Because for the Ziman effect, all of the states are actually degenerate states, because you will have what, 3 states in this case that correspond to the same energy level. Actually more than 3. You have 1 in here and 3 in here and 5 in here. So you have a lot of states in here that correspond to the same energy level 3. If you follow this calculation in here for the energy, where is it? Here. So all of them correspond to n equals to 3. So it seems like I have only one energy level that can be described with so many different wave functions. All I did is just write one of them in this case for this state. Okay, and that is actually a non-degenerate state, the ground state in here. It only is described by n equal to 1, L equal to 0, and mz equal to 0. It's actually the K state, this shell. Okay, the K shell. Anyway. So when we apply a magnetic field, as I was making a point earlier, it seems like this state's now split up. So how do they do that? So let's think about the electron. The electron in its motion around the nucleus. So it's a charge moving around the nucleus, and a charge moving around the nucleus can be interpreted as a current, which is the charge divided by the time it takes for the electron to go full cycle. This electron is moving so fast, okay? And the time for it to go full cycle is actually given by the radius, but the perimeter divided by the velocity. So it's 2 pi radius divided by the velocity. Okay, and this is basically in a nutshell how you can find how you can express this expression. So the current then in this case it's E divided by 2 pi r times V. Okay. So that is the current. Now, if I can do that, then I am going to assume, I'm going to calculate the moment, the dipole moment in this case, mu, and the dipole moment is that this current times this area. And the area in this case is just pi r squared. This is from way back when we were doing magnetism, okay? So this is, that is because you have a current now in a loop, and that is basically how you can calculate the dipole moment for it, okay? The dipole moment is similar to the electrical dipole moment that you guys also did in physics 2, where you can find this magnetic moment. In this case, it's current times I. For the case of the electric field, it's P is equal to what? Charge times twice the distance between the negative charge and the positive charge for the electrical dipole. Anyway, hopefully this will ring a bell. If not, just go ahead and review the stuff from physics 2. So the area is pi r squared. So if I do that, the pi cancels, and that's good because we don't want a pi in this expression. We already have enough pi's. So it's V times pi r squared divided by 2 pi times r. Cancel the r with the r and the pi with the pi. And now it looks like this expression is EVR divided by 2. Okay. If I multiply the mass and divide by the mass, well, MVR, or MRV to be more specific, MVR, yes, that's correct. That's the correct direction. So this is a linear momentum. This is R. Normally what I touch as RMV. This is actually the angular momentum L. Okay. So this is the angular momentum L. So the magnetic moment now can be expressed as the angular momentum times the charge. So it's E times L. This is the mass, the reduced mass, I should say, but it's practically, If we follow Mr. Niels Bohr argument, that's the mass of the electron, which is really not too different from MR2. So, divided by 2 times the mass, okay? Mr. Niels Bohr argued that the angular momentum in this case must be quantized, okay? And his argument gave us the fact that L is some integer, and it's the same integer that he used in his formula for the energy. That's how we arrived to that expression that looks awfully similar to this one. The advantage of this one in here is that you don't really need any artificial. All you need to do is assume Schrodinger's equation, and you're in business, and we found the same result. But for him, he really had to make that assumption without any solid arguments for it. But he found the correct answer in terms of the energy levels only, but he did not find anything else other than that. So there is a problem with this expression, because it looks like, if I use this one in here, that the dipole moment in this case, the magnetic moment in this case is going to be E times h bar divided by 2m times n. For n equals to 1, this number is going to be equal to eh bar over 2m. Now, this is for the electron. If I plug in everything for the electron, the charge for the electron, the mass for the electron, Maxwell constant, this number, of course, has the units of, because remember, when we're going to do the energy, U is just mu times B. Okay, those are two vectors. This is a vector, actually. It's along the direction of the angle, direction of the area, I'm sorry. And B is the direction of the magnetic field. That's why we're taking everything that is actually parallel to the z-axis, so that mu is actually parallel to the z-axis. And at the end is going to pick up actually the values for mz, as we were doing the calculations earlier. Anyway, so the problem with this one, so this is going to be a constant now. It's called actually mu b, Bohr's magneton, and the numerical value for it, because this is in joules, this is in Tesla, so the answer is going to be in joule in Tesla or electron volt in Tesla, so whichever you like. So we're going to get it first of all in EV, which is 5.8 times 10 to the negative 5 EVs per Tesla, or alternatively, actually it's 10 to the negative 24. 9.3 times 10 to the negative 24 joules per Tesla. Okay, you can convert yourself that it's actually an ampere meter second just by using basic formulas in here. So it is expected even for the ground state in here to have splitting if you really put it in a magnetic field, because that corresponds to this up and down in the energy. So the energy should be shifted, but that's not what was observed. It was observed only for the other energy levels. And now we have a problem. We couldn't really explain, because we have so many splitting and so many broadening to Ziman effect, we couldn't understand them in terms of Niels Bohr model. Because again, I'm just going to take B along the Z direction. B is equal to BZ K hat, if you like. So in this case, I'm going to just be dealing with the mu in that direction, which is going to pull me the component of the angular momentum in the Z direction, namely LZ. So the energy now is going to be split according to minus mu of B, of course, times this integer now that we're going to pull instead of n, we're going to actually pull mz in this case, times B. Okay, where mz is that integer that give me the splitting of the different levels. Obviously, if mz is 0, there is no splitting in here, so that corresponds to all of the states, of course. So there is no splitting in any of this because mz is equal to 0. Anywhere we have in here, we have since mz in here is equal to plus or minus 1, so potentially that level is split into 2 in additional to this level where you have mz equal to 0. So mz equal to 0 stays by itself, and you have above it 1 magneton, and you have another times B, and you have another one that is another magneton times B below it. Okay, in this case you will have 5 actually. You will have the one that is not split, and then you'll have 2 on top of it, one corresponding to plus 1 and another one corresponding to plus 2, and below it also you'll have 2. For this one you will have more, actually you will have 7. theoretically there is a lot of basically splitting for this lines under the magnetic field. And but what can you observe actually in an actual measurement? What can you do when you're actually measuring so let's take a typical transition from the 3D level, doesn't matter, to a 2P level. Okay, so the energy in this case is coming from n equals to 3 to n equals to 2. Okay, so obviously if I look at this energy level, in this case it's split again. This is P equal to L equal to 1. So that is actually mz equal to 0. And then above it, there is another mz equal to 1. And another mz in here below it that is -1. Okay, both of them, they will give you a slight increase in energy that is equal to mu b times 1 and negative mu b minus 1. So it's this number that I'm looking at in here. Okay. And mz can be positive or negative, so this number can be a positive or negative. Okay, so if I look, for example, at the 3D has several levels. I have 5 of them. So again, I have this is the energy level that has mz equal to 0. This is mz equal to 1. So it's just this number times 1. Now -1 if you want to put it on top. And then I have another one that corresponds to mz equal to 2. Below it, I have 2 more levels, mz equal to -1 and mz equal to -2. Okay, theoretically, the electron, once I have once I have put it in a magnetic field, first of all, its energy level is not the same. It's shifted by this amount. So we lifted the degeneracy that we were talking about earlier, in the sense that when I put the atom inside a magnetic field, now all of a sudden that atom now has different energy levels than for different p's and different different values for L and M. So now those states, they are split now, they are broken apart, so they are not the same energy level before the magnetic field. So this is basically, in a sense, the field zero field behavior of the atom, and now this is basically the behavior of the atom inside the magnetic field. Now these transitions are theoretically all possible. I mean, you can go from here all the way to here if you like. But that is not acceptable. It's forbidden. Let's say why. This one is acceptable. Up to here is fine. Okay. In here also is not acceptable. In a sense, because this transition from this energy level to this energy level require, of course, a photon, and of course, a photon has to carry with it a momentum. And because of a conservation of momentum, you cannot have this transition. So the transition must require that delta L must be equal to 1. Okay, and also delta mz, the change in mz must be also equal to 0 or plus or minus 1. If you do that, then you're in good shape. Then you can do this one. So this is called the selection rule. And actually at the end, when all the dust settles and you can calculate all of them, you will find that there are only 3 actual transitions that you're going to see in a spectrograph. Okay, this is fine and dandy when you have a magnetic field, but what was observed in Stirling-Gerlach experiment in 1922 is the fact that even in the absence of the magnetic field, there was actually a finer division, and that finer division now could not be interpreted with the fact that you have an external magnetic field. So what the theory is then was that, look, in this electron and its motion around the nucleus, what we neglected to do is the fact that the nucleus also is actually moving, so it's behaving like a current on its own right. So even in the absence of an external magnetic field, the proton will have magnetic field of its own motion, and that magnetic field will induce this separation. So that was the interpretation for it. That behavior in this case is not really fully accountable for the whole value of the spin. So in this case, what we're going to do is we relied on another approach, and that approach came way back later on by Mr. Dirac, including basically corrections from relativistic motion, because this motion in here is so fast actually that relativistic corrections, they will have importance. So when he included that, the value that was missing, the spin came into play. S came into play. So that is what Stern and Gerlach experiment revealed. So the spin now is another component. So instead of talking that the angular momentum is just due to the orbital motion, so this is the orbital motion of the electron around the nucleus. Now we have another component to it that is due to internal motion that we can't really express in a it's a vector too, of course, okay, in a simple fashion, okay. When we do that, now the contribution of the spin to the angular momentum is actually twice as much as this value, okay, twice as much as this value. And that is kind of fascinating because experimental observation showed that it's 2.0032. Experimental value was 2.00232. And then when Mr. Feynman actually added the contribution into the calculus, because there were some integrals that were really messing things around and people didn't know how to get rid of them. So when he came up with his approach, and then QED, quantum electrodynamics, came into play, which is generalization of this theory, including basically electricity and magnetism. So that gave us a value, and I would write it for you guys because I don't memorize it. And it's a very, very, very fascinating number, okay? So the value for how much the spin, basically the magnetic moment due to the spin, mu z basically, to spin, due to the spin, is of course going to be, as I said before, is some number in here that I'm going to write it very quickly, times the charge of the electron divided by 2m times sz, the components of the spin in this case, which is h bar. It turns out that this value has to be 1/2 of h bar, okay? Because the experiment itself was indicating that there is an even splitting. Because if we did this experiment in here, as you can notice in here, there is always an odd number of states, okay? What is it? There is always an odd number of states in this case. So there is 3, there is 1, 3, 5, 7, I mean 7 in here, so it's always odd. So but the experiment was indicating that there is an even one for of them, because in this case, if you do the calculation, mz must be equal to 2l plus 1 basically values. For l equals to 0, 2l plus 1, that's 1. For l equals to 1, 2 times 1, that's 2 plus 1, that's 3. For l equals to 2, 2 times 2 plus 1, that's 5. For l equals to 3, 2 times 3 plus 1, that's 7. So that is basically the way it's supposed to be. It's supposed to be an odd number. So when they did their experiment, they found an even number. So for us to have an even number, this spin must be half integer. Okay, hence the electron is called a half integer spin particle. It turns out, and there are other experiments, that's how also is the proton. So this is the electron and the proton. And something even weirder, the neutron also, that does not have a charge. So you cannot really give that explanation that it's a particle spinning around, because even the neutron that does not have a charge also have a single spin, half an integer spin particle. So all of these particles seem to have that. So that explanation that somehow it's similar to how the Earth moves around the Sun, like the electron moves around the proton, and then the electron is actually spinning somehow like the Earth is spinning, is not actually a good picture, is not the right picture at all, because it's quantum mechanics first of all. And then how are we going to explain the neutron? It doesn't have a charge, it has a spin. So there must be something else going on in here for these things, okay? So the value that QED has left, quantum electrodynamics has given us, this needs to be written, electrodynamics. Okay, this is the E, this is the D, this is the Q. Okay, is the following. Okay, so this number in here in between parentheses that I was talking about in here is 2.0 231 9 304 6182 14 digit precision. this is the most precise science ever that was invented by men, because it matches the experiment to an immaculate accuracy. Okay, so of course QED is a derivation of quantum mechanics. So that's why quantum mechanics is really one of the most reliable. It's unmatched. Nobody else can come up with this much precision, okay, in anywhere, whether physics or any other field. So again, if we do this analysis now and include the angular momentum, so now the energy seems to be given with a different value. Now let's include the value of J now. So J is going to be square root of J times J plus 1. The whole thing is h bar now. This is with the value of the spin included now. This is the J, which is just the sum of the two vectors. Okay, so if we do that, then of course we have the actual energy level now that depends both on N and J, and this explains the secondary Ziman effect, in a sense that the energy level is not just dependent on N, as we were thinking, even in the absence of an external magnetic field, is 1. So this 1 is actually the zero field basically value. That is when you don't have this whole thing is zero field value, okay? Plus alpha squared, and that's another interesting parameter, divided by n squared in this case, times n over j plus 1 half minus 3/4. Wow, it's an expression that is, you have to look it up to write it down. Okay, N and J we know what they are. They are the energy levels. So this does not depend on L. Okay, it depends indirectly on L through J. Okay, so the J is a combination of both L and S. Okay, so and you can find the maximum value and the minimum value, and that should give you the broadening, and that should give you the secondary. So when you're doing this problem for your problem, so just find the maximum, which is just L plus 1/2, and the minimum is going to be L minus half, and that's going to give you the splitting of the energy level at the energy N. Okay, what is that alpha? Alpha is a constant in SI. It's equal to 137 point something. Okay, the only thing I remember for it is 137, and this is the fine structure constant. And again, there is tremendous precision for it. 137 point. What is it? Going to ignore 0.04. Okay. If you don't remember the decimal point, that's fine. Okay. This gives us the ratio actually of how strong the nuclear force is against the electromagnetic force is. Actually, as a matter of fact, that this is the fine structure constant. Okay, because we're including now other things in here. So this is the fine structure constant. Okay. So now what happened when we don't have really a hydrogen atom, but we have a bunch of atoms? In this case, you'll be tempted to do the following. Assume that all the electrons are moving under the same central field, because central protons, because you'll have Z protons in this case. And assume that each and every one of them, so this is the nucleus, and you have Z protons now, not just one, Ze plus. And you have, of course, a bunch of electrons floating in here, so you can take Schrödinger equation for each and every one of them and solve it, and that is not good. It does not give you a really good result. So instead of what you do in this case, you do an approximation, and it's called the central field approximation. So what that is, you're going to treat the atom as if it's made up. Of course, again, you have the Ze plus, and you have those electrons in a cloud interacting with the protons inside as much as they are interacting mutually. Okay, so there is an interaction that you cannot neglect between the electrons and themselves. So there is a repulsion, actually, an electrostatic repulsion between this electron and this electron in the structure in there. And if you do this approach, you will find that the more or less the NL, M, NL, and MZ, and also SZ now, the component of the component of the spin in this case also will be included in this problem. So more or less that way, except now the energy really depends on L2. So those energy levels now, when we compute them, they will have an L in them, and that is a very important point in here, because this energy levels, the one that I was writing earlier, where are they? These ones in here are not filled in this order. They are filled actually in a slightly different order. Furthermore, Mr. Pauli actually discovered something else, that in order to explain what's going on with the periodic table, we have to include something he called it the exclusion principle, and that actually is what is going to be the last thing that we're going to need to have so the exclusion principle that bears his name now. So this is the Pauli exclusion principle that says no two electrons can have the same quantum numbers, meaning they cannot exist in the same quantum state. Meaning they cannot have the same wave function. So if they have the same n, they cannot have the same L. If they do have the same L, they cannot have the same mz. And if they do have the same mz, they cannot have the sz. End of the story. So one of them has to give. Okay. So in going through basically the structure of the atom, you can go through the periodic table, and you go from left, from basically the hydrogen atom. There is one electron that you can put in the sorry about that. Anyway, so basically when we start filling, we go from the hydrogen atom. Of course, the hydrogen atom has one electron in the S state, so we're talking about the fundamental state in this case. So we have one electron in the S state, we're fine, okay? And then when we go to the helium, in this case, we have two electrons. So theoretically, the two electrons in this case, they can exist in the same S state, provided, because the S state in this case has n equals to 1. Albeit this n is not exactly the same n as for the hydrogen atom. I mean the energy itself, the actual magnitude of the energy. Now the second electron will have actually it will have, both of them have L equals to 0 and mz is equal to 0. But in this case, one of them will end up with an sz that is plus, the other one is 1/2 of m, 1/2 of h bar for the moment, for the spin. So in this case, we are fully, in this case, saturated. There is no problem with it. The next atom, that is going to be lithium, in this case, will have 3 electrons. So if we do 3 electrons in here for lithium, so again, the first 2 electrons are going to be exactly like they were going to fill the energy 1s, and both of them are going to be there. Now the next electron that we're going to add must reside in the next energy level, which is the 2s. Okay. If we follow the periodic table, the next element is actually beryllium, and beryllium will have 4 electrons. So beryllium has the first 2 that are filled like the hydrogen atom, and the next 2 are 2s2, and in this case the beryllium has 2 electrons in the outer shell. Okay. The next element in the periodic table is the boron, and there is a big gap in there, and there is a reason for it. There is 5 electrons. So again, we're going to follow that. It's 1s2, 2s2, and now we need to jump into the p state. So we have 1 electron in there. You don't really need to write it, but there is an electron in there. The next element, of course, is going to be 1s2, 2s2, 2p2, and you're going to finish until you end up with 2p6 at the end, because the p state has a -1 for the angular momentum, 0 and 1. So you start filling up the -1 first, then the 0, and then the 1. So you bring an electron in here and you put it in here. So this is 1 electron spin up. Okay. You bring the second electron in here, is going to actually go to the next level. Okay. That's 1 spin up. You bring a third electron in this case, that's going to be here, spin up. Then you bring the next electron in here, it must reside somewhere in here, spin down. And the fifth electron in here, that's going to be here, and then finally the state will be saturated by that one. What happened next? Instead of going to, no, actually we go to the 3 now. Okay, so we're going to move to the 3 now. Again, we're going to repeat the whole thing. 3s, fill it up to, then 3p, fill out the level. Then after that, something funny happened, and it has to do with the energy levels basically, and I was making an argument earlier for them. instead of going to go to 3D 1, no, you're going to go to 4S actually, okay? And you start filling out those levels. And again, it has to do with how the energy is actually situated when you do the actual calculations. The energy levels are sitting in underneath one another. They are not exactly like, it's like that it's like the particle in a box, basically, where we saw when we moved to 3, it was actually lower energy than that of the 2, 2, 2, 2. So depends on where the energy level, that's when you need to move. So that is basically an explanation of what's going on with the periodic table. And to finish this topic in here, basically for this one, is what's going on in terms of transition for the heavy atoms and the more atoms. When we looked at the X-ray radiation, because that involves the lower energy levels, we saw that this model is actually fully justified because there is a screening from the electron that we're going to put in there. The electrons that we're going to have to transition to the lower level, to the K level, is screened. All of the other electrons will screen the rest of the nuclei, basically the positive charge, the protons, with the exception of one, because we're lacking one. That's why basically we have to have that. So the dependency in here of the frequency depends on z minus 1, actually is square root of z minus 1, or I'm sorry, z minus 1 squared, okay? So when we plot that one, it's a linear function that grows, of course, with the different elements, and that's a perfect justification for this why this theory is acceptable. And the chapter closes with a quantum entanglement, basically when two particles have states, and when they migrate away from one another, they keep basically their information. So when you measure one, you will find as if the other one is actually responding at a speed greater than the speed of light. But that's another topic actually that has very little bearing in terms of what we need to do in terms of these problems. There will be another session on this one in here dealing with problems. So hopefully you will follow. So let me tell you what the problems I have in mind in here that I thought are of interest to us in here. Okay, let me go with problem 1 first. Problem 1 is going to be problem 44 from this chapter. So let me write them down. Where is my pen? Okay, so problem 44. And the other problem that I think we're going to explore in here is problem 52, problem 53, and I thought there is at least 2 more. Okay. Problem 63. Yep. And problem 60 also. Okay, depending on how it goes, okay, we may just have to stick with only 4 maybe. And finally problem 30. Okay, let's see here if we can do all of them. Okay. So again, I'm not taking them in order of any kind of increasing numbers or decreasing numbers. So please watch for the next recording concerning problems for this chapter. Thank you.